called the chain rule. So this is the chain rule, not for normal derivatives, but this time for partial derivatives. So for partial derivatives. So let's set it up a little bit. Let's say we have, so if we have an f of xy, so some function of x and y that's composed of, so again, chain rule is for composition of functions, right? One function inside of another, and we want to differentiate. So we have a capital F, that's our outer function, and our inner function is a g of x and y. Okay, so this is the inner function, inner, and this is the outer function, or the outside, outer. I'll just put outer, okay? All right, so what is f, this little f sub x? So that would basically be, so we have to go through the outside, so we're going to start from the outside and we have to work our way in, okay? So this is going to be the derivative, this is going to be the partial derivative with respect to x. So partial is actually denoted by these curly little d's. I don't even know if there's a name for them, or there probably is, but I just call them curly little d's. So this signifies partial derivative as opposed to the single derivative, which is a normal d. But anyways, so yeah, so the partial derivative with respect to x of f of g of x and y. So we're basically going to just like differentiate the first thing, the outer one, with respect to the next thing that it touches. So that would be the derivative of capital F, so the outer, with respect to the next thing that it touches, which would be the g. And then we can go from that point, so we're going to multiply, times the derivative, and this time it'll be the partial of g with respect to, and we want to get to the x. So partial of x, okay? So in this case, we see the normal d's, right, with the capital F and the g, because the capital F is just a function of one variable. We can consider this g as one variable, okay? Because when you plug in that x and y, we just get out one answer. So anyways, so that would be one variable here, and this is multivariable because we have two variables to choose from, our x and our y, and we're kind of ignoring that y. So that's why we have the curly d's there. Anyways, so this would be this is the chain rule, basically, the thing that I just did here. So it's basically working from the outside, the outermost function, and then going through the middle functions. So in this case, the middle function would be g. That's like our bridge, right? These two here. And then getting to the variable that we want, which was the x, right? Denoted here. Okay, so that's for f sub x. So now let's do f sub y. So that would be the partial with respect to y of our capital F of g of x and y. So here again, let's go through the steps. So we start with the outermost. So we're going to start with that f, that capital F. And again, we have that normal d because this capital F is a function of one variable of this entire thing inside of g. Okay, so df, dg. And then, so we made that first leap there. Now we need to get into the y part, not the x. We're ignoring that. So we just go dg, dy. Okay, so I guess you could consider it like whether you do the normal d or the partial d. And some people might not even be that picky about it or anything like that. It's just a notation difference. But what I consider is like if you're making these jumps, so let's say we were going to start back capital F, right? And then you jump to G, right? There's no other choice than G, right? That's the next closest. So that's why you have the normal D's. And then when you make the second jump, the second leap, you have a choice between X or Y because it's just separated by that comma. So then when you have a choice to pick your next variable, then you have to have that partial to specify which one you do want. Okay? So anyways, so these are the chain rules. It's a little bit messy. Sorry, I was circling things. But this thing there is equal to the partial with respect to X. And this thing down here is equal to the partial with respect to y, given our conditions up here, okay, in that line. All right, so now let's try an example of this chain rule. So we're going to compute the partial with respect to y of cosine of xy cubed. Okay, so here we definitely see a composite function, right? Our outer function is cosine, and the inner function is this xy cubed. So the inner function, let's label that g of xy is equal to xy cubed. And this outer function, I'll name that our capital F, right? And we'll say of g, okay? So this will be cosine of g, basically, okay? Excuse me. Okay, so we have our outer function. So this is the outer one, outer, and this is the inner function. And now let's apply the chain rule. So here we're going for f sub y, right? Because we see that from the partial with respect to y. So this would be the partial with respect to y of cosine xy cubed. So from our chain rule, we know that this is going to be the derivative of the outer. So derivative, not the partial derivative, but the normal derivative of the outer with respect to g times the partial of g with respect to y, to y. Yeah, I thought we were doing x first. But with respect to y, okay? So that's the one that we ultimately want to end up at, is y. So we're going to pick that one. And now we just kind of apply what we see. So df dg, what is that? So we're going to have capital F dg. That would be differentiating this guy. So that would be a negative sine of g. And we'll just keep the g in there for now. We will be replacing that again with what we see as what g equals with respect to x and y. But anyways, we'll just keep that there for now. And then we have this multiplied times the partial of g with respect to y. So that would be partial with respect to y of xy cubed, right? Okay, so now if we want to simplify a little bit, then we'll get f sub y is equal to negative sine g. And then let's see what we have here. Let's look at this guy. So if we're differentiating with respect to y, that means our x is being held constant. So we can bring that out in front and just not worry about it, right? So we have that x there, and then we have the partial with respect to y of y to the third. Okay, so that's just going to be a negative sine of g times x times 3y squared. Okay? All right, so now I'll move on the next slide and we shall continue. So f sub y is so far negative sine of g times x times a 3y squared. And now you might be like, okay, so what do we do with this g? That's just sitting there. So now we consider that g of xy is equal to x times y to the third. So that's what we're going to do. We're just going to replace this guy, x times y to the third, in for our g. So we're going to sub that back in. Okay? So f sub y is equal to a negative sine xy cubed times a 3xy squared. Okay? And we can always just rewrite this one more time just for aesthetic purposes. Negative 3xy squared times sine xy cubed. Okay, and you're always welcome, so this would be our answer, right? And you're always welcome to try to integrate. I wouldn't do that, but anyways, so you can always just go back and like do it over one more time to check your work and make sure you get the same answer, okay? All right, now we're on to, we went over some of the partial derivatives, right? With respect to x, with respect to y, and you do the same thing with respect to z too. Now, let's go over higher order partial derivatives.